Okay, let's take a look at two ions. We have the fluoride anion, and then we will also do aluminum 3+. Okay, if I look up fluoride in the periodic table, I'll see that it is element number 9, which means that I have 9 protons. And if I'm just talking about the atom of fluorine, it will also have 9 electrons. But now I'm looking at the ion, and it's a negative ion, which means it will have excess negative charge. And that minus, I don't have the 1 here, but it's implied. That number there, -1, tells me that I have one more electron than I do protons. So if I have 9 protons, for F1 minus, I will have 10 electrons. I'll have one more. 10 electrons is one more than protons, 9 protons. So now that I have the correct number of electrons, I can go over here and I can fill this out, doing exactly like we were for the actual atoms. I start with the lowest energy first, and I have to fill both of these, so to put 2 electrons in there to pair it up. And then I do the same for S. That's 2. I have used 4 of my 10. So now I can go in here and for these orbitals that have the same energy, I will put 1 in each one and then come back to pair it. So I have 5, 6, 7, 8, 9, and 10. I've used up all those 10 electrons. Now when I go to write the full configuration for the fluorine ion, it would be 1s2, 2s2, 2p6. This is the configuration for fluorine minus. I will use a different color. I will erase this here, and we will do aluminum 3+ and see where we get to. Aluminum is element, if you look it up in the periodic table, you will see that it is element number 13. Okay, so if I were to look at just the atom, so number 13, that tells me it has 13 protons. However, I have a positive charge, which tells me that I have an excess of protons. I have more protons than I do electrons. That means that aluminum has lost some electrons. And how many it has lost? That number tells me how many. So it has lost 3. Therefore, instead of 13 electrons, it has 3 less, which means that it has 10 electrons. Oh, well, it has the same as this one, but let's just work on filling that out just for practice. So I start with 1s, and it can accommodate 2 electrons. So can 2s, and I've used 4 of my 10, and then 1, so 5, 6, 7, 8, 9, and 10. I've used up all my 10 electrons. So therefore, when I go over here to write the full configuration, I would write 1s2, 2s2, 2p6, and then I end up there, and this is aluminum 3+. Now what else is the same configuration? If you look in the noble gases, you'll find that neon has 10 electrons. Neon will have the same configuration. So this, for both of these, corresponds to the neon configuration. So if I were to do the shorthand notation for these, I would just write neon, and for this one, the neon as well. Now notice something. That only happens with ions. It does not happen with atoms. Atoms will never have the same number of electrons because atoms will have the same number of electrons as they do protons. And the number of protons is never the same for two different types of atoms, two different elements. However, when we talk about ions, ions are formed from the original element by losing or gaining electrons, and they lose and gain more than one electron. Some might lose more, some might gain more, some might lose less and gain less. However, as we see here, for example, we have a negative ion, so we have an ion that gained an electron to get to neon configuration, and we have an ion that lost electrons to get to neon configuration. But both fluorine anion and the aluminum cation, it's a positive ion, so the negative ion and the positive ion both have ended up in the same configuration, that of neon noble gas. We call these ions isoelectronic with each other. They're iso meaning the same, so isoelectronic, same electrons, because they end up having the same number of electrons. And if you notice, they both ended up with the configuration of noble gas. That is because every element in the periodic table is trying to get to the configuration of a noble gas. And they do that by either gaining electrons or by losing electrons, depending on which one is closer. Fluorine, for example, is number 9 and is closest to the left of the neon, which means to get to neon, it has to gain 1 electron. And it does so, and it gains a negative charge. Aluminum is past neon. It has already passed it. Neon is number 10, aluminum is number 13. Therefore, it's past neon. So it has to lose a few electrons to get back to neon. Fluorine hasn't gotten to neon yet, and it has to gain electrons to get there. Aluminum has surpassed neon, has gone beyond neon, so it has to lose those electrons to get back to where neon is. So these are called isoelectronic, and remember that all of the atoms, all of the elements in the periodic table are losing or gaining electrons to try to get to the noble gas configuration, because noble gases are the most stable. And the reason is because they have full orbitals, full shells. They don't have, all of their electrons are paired, and they do not have unpaired electrons. They have full shells. So for neon, the level 2, so level 2 is filled. For argon was level 3, etc., etc. And so noble gas configurations are the most stable because they have full shells and they are not, they don't have unpaired electrons. Therefore, they don't like to react very well. They're very inert. And that is why every other atom is trying to get to that configuration, because that is the lowest energy, the most stable for all of the state for all of the atoms. Okay, I am going to erase this, and then we're going to continue on with the problems in the rest of the chapter.